All right, thank you, Jenny. So, first thing, we all need to go onto this link first. I can make it bigger for you. Step one, let's see if we fail at this. If we fail at this, we can just go and have drinks. Should be, oh, yeah. You can Google my name, and this GitHub is going to show up. So plenty of ways to like go to this link. Let's see if it works. Yes, that's what it should appear. I don't hear typing anymore. Assume everybody made it. Yes, there are other two links because it's pointer to pointers. We go to the binder link, which is the second one, which is this one. Yes. And while this thing is loading, because it's going to take a while, so while this is going to like do stuff, I'm going to just make some jokes. I was really amused when I saw the timetable for FOAM, because it's like I'm the final boss that is standing between you and drinks, or between us and drinks. So like, find it really amusing. And I had actually an alternative title for this presentation, is How to Shorten Coffee Breaks, the Minimal Playbook. So how many of you like to drink Americano here? Okay. If you leave now, I will not judge you, because you're going to switch to espresso by the end of this. Like you won't have time to drink a gallon of water. Like you won't have. So no, this is like the joke I was trying to make, but the PNG on the website is really low resolution.
There's a non-zero chance that something is wrong with this TCSD binder.
Okay, so if everything goes well with binder, I made it work. If something goes wrong, it's Dylan's fault. Okay, this is the agreement. All right. I actually now need binder to work. If it doesn't work, okay, it's waiting for a server. In the meantime, we can look at my my Python notebook, which should be also here. At least mine is committed here, while hopefully it loads and does something on your side. Okay, now do I have a way to make this full screen? Good enough. And color map is reversed. So hopefully binder loads up for everybody while I'm doing this. Otherwise, like Robert is going to tell us what to do. Okay. So who was here for Alex's talk this morning, first in the morning? Okay. My prompt to Alex is I'm going to speak about recurrence sequences, and I guess I told you about polynomial evaluation and things like that. Everything else kind of like has been a good introduction for what I'm going to present here, but we haven't actually coordinated. Everything was vibe presented by Alex. I gave a prompt, and he did everything. Yeah, a little bit more efficient than that. So one thing that amuses me is that just on the first slide, we have I0 here as a function, which is one of the functions that is showed that on some older books you will find as a table of number, and by hand you have to do linear interpolation when you need it. So what exactly this function is doesn't matter. What matters for the purpose of this presentation is that this function uses I0, which is a Bessel function of the first kind, of order 0. That's what it means. And this is a fairly recurring function that is also fairly expensive to evaluate if you look at the mathematical definition of this function. And so when we encounter this thing, which is very common, how do we make it go fast? How do we avoid waiting a long time for my code to do whatever I asked him to do or my agent asks it to do? So you can see the definition. It's like it's not trivial. The amount of flops you need to do to evaluate this usually is approximated. And the input terrain is 0, 1, which, like if you listen today about centering your polynomial in -1, 1, now you realize why I chose the Kaiser-Bessel kernel for this thing. But if we actually run the script, okay, and we want to just evaluate this thing, we have a bunch of boilerplate because it's Python. We have another bunch of boilerplate to benchmark how much it takes, and then we finally get to NumPy, which we have seen already today in multiple different ways. And the way that the math translates to Python is basically these 6 lines of code, more or less. And I remove there is still the clumping, but this is not needed. This is never going to happen in practice. Now, OK, this is something I have to run, actually. I was not expecting this not to happen, so maybe I'll run it locally at this point. I don't know. Like, I can check. Oh, yeah, that worked. So
we have been fighting with a problem user who keeps killing Binder. And they're like, no, I'm doing the right thing. And we're like, no, you're not.
All right.
They broke it again.
Oh, OK. Now we actually can see stuff happening. It's big enough, I think. OK, and this is the graph of the Bessel function, of the Kaiser-Bessel kernel. It's a very smooth function that goes from 1 to 0.4 in this case, something like that. Not particularly fancy or interesting, but it's there. And if you actually look at how much time it takes for this many evaluation, you can count the zeros if you care about. It takes about 13 seconds. And in million of eval per second, we do 0.07. Like it's very slow. It's really bad. This is Python. How many of you hate Python? OK. Only half of the room. I gave you a chance to cut my talk in half now and go to drink first, because if the majority was saying we hate Python, we will just go and have drinks and forget about this. OK. I guess you're stuck here. I assume that you're all motivated for my exercises now, because I gave you 2 chances of bailing out and you didn't. OK. So what can we do to make Python go a little bit faster? Well, we can use C++, but if we use C++ directly, then we have to do a lot of binding and boilerplate, and it's not really a fun thing to do. This is what AI agents are for. But I discovered that we can actually JIT JIT C++ into Python, and we just need to write the bare minimum of C++, which I'm also happy with, because I do like writing C++, but writing a lot of it is not really fun. So what I've done here.
So it's kind of interesting that the I0 Bessel function is part of the standard library for C++.
Yes, exactly.
That must be kind of a new thing.
It is 10 years old.
As I said, a new thing.
Yes. So because I cannot control the compiler flags here, I added some pragmas. You can copy paste them. These are pretty safe in any code. But then, to implement Kaiser-Bessel is the same amount of lines that I needed in Python, which is really good. I just needed include CMAT. I mean, I have import math in Python, import NumPy and all these things. But it's a 5-liners, OK? And then I can basically use cppyy global Kaiser-Bessel, which is the name of this function here, this QMatch. I pass by casting to float in this case to tell cppyy that these are double precision, because Python floating point are double precision. And that's it. OK, now this thing runs, compiles on the background, does a bunch of things. If I plot it again, we see that they perfectly overlap. I could have been smarter and use different dots and stuff to make it show that they actually overlap. I'm too lazy. Okay, so and when I start to evaluate, okay, now this thing took 0.12 seconds, and it does 2 orders of magnitude more million of eval per second, which is about 100x speed up. So if your code was taking 100 minutes before, you had all your time to zip your Americano. Now you don't. You have 1 minute. Okay? And this is one way that we can do that. The other way is go the JAX way, I guess, which is Numba and JIT. Another way of JIT in Python to make it faster. Now, we haven't changed anything here. We kept things as they were. But because I used ngJIT, when I try to run it, actually, it fails miserably because I disallowed to use any Python in my kernel. My kernel has to be only C++. And the problem is that I0 is not being numbified. I guess that's the correct technical term. Okay, so has not been numbified. Okay.
And that's because it's numpy and numpy.
Oh yeah, you can use SciPy. Like if I switch to SciPy here and I do the same error. Problem: this function has no support for jitting. But then I discovered that I can add one line here, which is import cppyy numba extension. And whatever I do in cppyy, I can use it inside numba. So now my Kaiser Bessel is like my Bessel function is like 4-liner, okay? I keep my Python code as it was. The only change I do is say, okay, use I0 that I just gave you, okay? Yeah, don't try to use NumPy, don't use anything. Use the one I gave you. Okay, now we go ahead and we say, oh, it actually worked. And now we have a nice plot. And now we have 3 perfectly overlapping plots. So I guess I should have plotted in 3D. Okay, what's the performance? Basically the same as writing in cppyy. So my first takeaway, if you like jitting, with all the problem of the person using this code, it also needs a compiler and everything. But if you run the code on your machine, you control your environment, or on the cluster here where compilers are available, and first of all, you run on Linux. You don't use whatever thing that is not. Oh, macOS is fine. You can use that. I concede on that. But if you use all of these, this is pretty seamless. And with just a minimal change on your bottleneck and say, okay, this is my bottleneck, just do this in C++, you made your code 100 times faster, which I think is quite a good thing. I don't know. Who agrees with me? Who likes this so far? Yeah. Okay. What's questions? Like, what's the catch or something? Nobody asked that, Okay. Nobody wants to know what's the catch, so let's go on.
So what's the basic reason we're getting such a massive
Yeah, because you're basically running native assembly. You're not running through the Python assembly, the Python interpreter. And second, is also using O3 and March native. So it's doing vectorization if possible. Method 4.
Oh, sorry, Marco.
Yeah.
So I guess the Bessel function implementation, the standard, is not guaranteed to be most performant.
Is there a standard?
In C++.
Oh, yeah, no, that's not guaranteed to be
probably can get.
We will get there. Okay, yeah, we'll get there. This is actually method 4. Okay. A lot of you were here when Alex was giving his talk. So now we start talking about Chebyshev, and this is going to be a recurrent theme of this thing. There is a book somewhere that said moral principle number 1 is if you're in doubt, use Chebyshev polynomials. If you are not sure what you're doing, use Chebyshev polynomial, and something like that. I have a tab somewhere. Like if I have time, I'll show you. Like it's really amusing. Just use Chebyshev polynomial. When you're in doubt, just use Chebyshev. Okay. So what happens if you use Chebyshev? We can use Chebyshev entirely in NumPy. We do a Cheb fit, and then whatever this API is doing, poly. And we have like has to do this polynomial evaluation here after the fit. Okay, this is not.
So wait, what's ch dot? Yeah, what's ch dot fit? Is that?
Yeah, import NumPy Chebyshev as ch,
Okay.
because it's too long to write every single time.
Got it.
It's all NumPy here, it's all Python. I haven't done anything. Okay. This thing also does what I asked it to do. It's, pretty accurate because I said I want an expansion of 16, which in this case is enough for messing precision. What happens here? Okay. It's only 24 times faster. It's not 100 times faster. So I guess Alex lied to us today. Okay, not as simple. I know I cannot make my boss look bad. So so what happens if I implement Chebyshev now? You don't need to do that. Just don't do this. I'm just showing you an example. Now I write all the Chebyshev code. It's like 50 lines to 100 lines, and I do it in C++ YY. Okay, I defined all my Chebyshev expansion, everything. Now I do my binding here and everything, and I have my Kaiser-Bessel Chebyshev function. Okay, this works. Trust me. This is what happens. And whoa, where is the timing?
You didn't add the timing to the.
Oh, I didn't add the timing. Okay, then there is a spoiler. You'll get it later. You have another method that is easier. Okay. I guess. So another way, instead of writing all the code that just showed you, which is not the most optimal way of doing this anyway, but it's pretty good, is to leverage the work that someone else did and figure out all of this for you. And there is a library that Robert made called Baobzi, which is 5 lines for the input parameters, and then 1 line to define it. You just define these parameters, and then you just pass it. That's it. Pretty easy. This is as much code as you need to write. This also gives you things that are perfectly overlapping up to machine precision in this case, and is really good. And now we can see the performance. Okay, so I want to scroll down, not to spoiler. Okay. Okay, whatever. Okay, I cannot do that with a touchpad. Oh, why my touchpad is going crazy? Okay, so if I implement in C++ Chebyshev, I get 500 times faster speed into this thing, which is, I would say you don't even have time to leave the desk at this point. This thing is pretty fast. Bob's is only 55 times faster. But there is a catch, okay? There is a catch. As you might have noticed, I wrote some pretty bad Python. This Python only evaluates 1 point at a time, while usually in Python, to leverage NumPy, you will pass, okay, this is a big array. Evaluate all of these at once. This is how it usually works, because then it offloads to C++, you pay the cost of offloading once, it does a bunch of vectorized stuff under the hood, you get the result back. Okay, I wrote all the code to do all of this, so I can tell you I know how to write Python, I'm not that stupid, okay? And if we look at the vectorized version, where we say all these methods now are going to evaluate 1,000,000 with one single function call, instead of doing a Python for loop, which is also bad, and it terminates with an exception. It's Python things, I don't understand them. And now we get to the actual thing. Okay. If we use the vectorized version of NumPy, implement Kaiser-Bessel, and they say this is a vector of a whatever n is over there, 10 to the power something, and evaluate it at once, now we go to 3.4 millivolts per second, we were at 0.007 before, just to remind you. So this is like a little bit faster. Now we say, OK, CPPYY, but do that also in a vectorized fashion, 4 times faster. Sorry, 4 seconds, 2.4. Yeah, so it's now actually got slower than the vectorized version of NumPy. Jitting with Numba, same thing. Now the vectorized NumPy is faster. But then I said, OK. I cannot be defeated, no? So I implemented, so this is the Chebyshev version of using just NumPy, which is 7.4 million, which is 2.5 times faster. So Alex didn't lie to us. You can use Chebyshev and very good speed and accuracy as well. OK, but then I said, OK, all these things is fine, but now my code is slower than everything else. So I said, OK, let me write the vectorized version of that in C++ YY, instead of doing the for loop in Python, now we do the for loop in C++. Just that's all the change, the only change I made.
Now, by vectorized, you mean it's just going to act on an array?
Yes.
But you're not using it in this more technical sense of SIMD?
No, I haven't manually SIMD'd anything.
Okay.
I rely on the compiler doing it for me, in this case.
And how many, is there any thread parallelization
No,
occurring?
all disabled at the beginning.
All single thread?
All single-threaded.
Okay.
All single-threaded. If you also add the thread parallelism, which is one parameter in Numba, parallel equal true, then you get also that for free. So yeah, this can be also much faster. Like this is just an example. But now what happens is that we do 38 million eval per second, which is about 11 times faster than the vectorized version of NumPy, which, a 100-minute coffee break now is at 10 minutes. You can probably have like a cappuccino or something. But then we say, Robert, can you optimize this for me? And then we get to up to 26 times faster, at least on the machine I run this on. Which I think is pretty good for something that you just pip install a library, you write 5 lines of code, you pass your function, and that's it. This is, I think, like a pretty quick way. I think I showed you like 4 or 5 methods, maybe, where you can get like 2 orders of magnitude more performance for what you're doing with minimal code changes. Like, did someone learn something new here? Yeah. OK. The questions? OK. Oh, yeah. OK, good. Sorry?
That's all Babsy does. One thing.
One thing, but really well.
Very well. It's a Unix library. It fits currently any input dimension function to a 3-dimensional, 2-dimensional, or 1-dimensional output function. We have a new version on the way that maps any dimension function to any dimension.
Yeah, and we also are going to simplify the API a little bit to make it more natural to use.
Cleaning it up, make it easier to use.
Yeah.
Possibly add Numba awareness so that you could throw it in Numba, stuff like that.
Yeah. But, this is the point. Like,
well, I'm still going to ask an annoying question then, which is like, do you know if it was using one interval, one Chebyshev interval?
Bobsy?
Yeah.
I don't.
For a very smooth function like that, you should be able to do it with one interval. And then there's no. The question is there's any overhead for like sorting the X points into the bins that they belong.
So what is
anyway,
the?
Right. Okay. Because you should still be able to get down to nanosecond.
Yeah. Maybe. Yeah.
I don't want to slow things down.
Yeah, I don't think now we have time to that because I'm looking at the timer and we're already out of budget. So we might scrap the old C++ part But now we want to try these things. So exercise, we open exercise. We run it all from the beginning, OK? And by the way, CPPYY doesn't play really nice on binders, so you might need to like rerun the whole code base because you try to compile it twice and it crashes. Now we have a simple physical problem. I don't really want to go over the math. I don't think we need to understand the math really to use this. There is an analytical solution to this problem. This is what we are interested, that uses the modified Bessel's functions, I0, I1. Okay, so you saw one solution for I0. You basically need to copy paste it and change a number for I1. Okay. So if we run this simulation and we do all of this, we get up to a point where we get some nice plots here. That just to show you, like, this is a lot of like boilerplate. But then we get to the actual exercise here. OK. This is the function that we need to make faster. The steady diffusion cylinder underscore I called JIT. You know, I wonder why I called it JIT. Spoiler, no spoiler. So what does this thing does? Computes I0 twice on 2 different parameters, couple of multiplication, and a division at the end, like a couple of divisions. Like, that's all it does. If we run the exercise as is, the solution is correct because the JIT function does the same thing as the normal function, so we haven't introduced a bug yet. This is the whole point of today, no? And OK, now there are like, I don't know, we are here 50, 60 people like that we are using the machine. So the execution time is not perfectly equally like at the moment because everybody's on this machine. Now, the exercise is use whatever technique you've seen in the oh, where is the actual exercise? So this, OK, yeah. Change this function as much as you want, OK, just to make it faster. So, question, how many solutions do you have for this exercise? I do not open solution yet. I'm not sure that my solution is the solution, is a solution. Like, according to you, what's the easiest among all the API I showed you to do this?
Maybe, but it sounded like the easiest thing was to actually send in arrays instead of scalars.
Yeah, I don't wanna like.
Are we going there?
I don't think we have time to just send arrays because then you have to steal the memory from NumPy if you wanna be fast. Mm-hmm.
Yeah, so about the previous notebook, so why did jitting slow things down?
Why jitting slows things down?
NumPy in the vectorized?
Yes, the short answer is because the C++ standard implementation of the Bessel function is complete garbage.
No. I'm comparing the number JIT and NumPy for the vectorized.
Yes.
Yeah,
The standard, the C++ standard implementation of the Bessel function is bad.
So the one that number JIT pulls?
Yes.
Oh, okay.
Because we told them to.
Okay.
If I put a faster implementation, which, for example, Boost, that thing is already faster than NumPy. It's just because the C++ standard implementation picked the slowest among all possible implementations.
I see. But in the scalar case, it was good enough.
Yeah, in the scalar case, it's still much faster than pure Python. In this case. My usual way of going is do the easiest thing first, always, and if needed, improve upon it. So like if you're doing scalar, try scalar and see if you're fast enough now. So if you still have a coffee break, you have time to like optimize your code. If you don't have a coffee break anymore, then you can leave it as is. That's the rule of thumb. OK, I can answer any question while you do the exercise. So I'll give you, let's say, 5 minutes for this exercise. And then we move a little bit on C++ and see how far we get there. Yeah, you're allowed to copy paste code from my presentation to here, of course, you know.
I'm copy pasting into my text interface to Python. Isn't that?
Oh yeah, that's totally fine. Copy pasting code in exercises is fine. In production, probably not a good idea. Of course, there are emojis and there are things that I will never put in my code. But you know, this is not production code, and generating a physical problem doesn't take much, but you know, all the plotting is pretty annoying to do. Oh, another thing that ChatGPT did is to move stuff around into my slides. You know, it's very annoying to position an image in LaTeX. So if you ask ChatGPT, how do I move this around? Usually it tells you stuff that is useful. Okay, this is about time now. This someone hasn't finished yet. I only see one person coding from here. So how many did not finish? 2, 3, 4. Okay, so we have like 4 or 5 people. Let's try for a couple of more minutes. Yeah, run locally is a bit annoying. You need to install the dependencies. There is a requirements file into my GitHub repository for that purpose. But like you're faster in just using binder, probably. Or pip install everything. If you have a problem with your compiler. Okay, there is a conda YAML then in my. Okay. Okay, I think we can move to our solution here. So how many of you use the Numba to try to make this faster? How many of you use Numba? Okay. How many of you use Bobs instead? I am pretty disappointed. I'll have to say. Okay, so solution. I'll have to run it, I guess. Did I click the correct button? Let's see. Okay, let's make into it. So What I've done here is a little bit overkill because what I've done is I know how this function behaves. I know the plot of this function of the Bessel I. So if this function is between 0 and 3, I use Chebyshev. Otherwise, I default to the standard library implementation of it. Does somebody know why I did this? Okay. Because if I were to fit it on the whole domain, I cannot get away with just an expansion of 16 terms. I will need way more terms to capture the oscillation, the actual pole that this function has after a certain threshold. But I also know that this simulation, this is another trick I'll tell you, most of the time it requires values between 0 and 1 when it calls I0. So I basically optimize for the average case. On average, this function is going to use a Chebyshev implementation because on average it requires value in that domain. When it cannot, it's just going to use the standard library, and this way I'm fitted on the whole domain, and I can be really fast on the average case because I have a very small Chebyshev expansion. And OK, we can test that this thing is correct. The maximum absolute difference is like machine precision, basically, a little bit more. And this is how the speed compares. We are 2.5 times faster, with a throughput of 30 million instead of 15. And this is like a result that it's not great because on this machine we are contending for resources. If I might have the solution already here with populated when I run it on my laptop. No, I didn't. OK, so but on my laptop, this thing is usually 10 times faster than pure Python. OK.
So I forgot, is the test using a vector of an
No.
array or no?
No. It's just on a scalar.
Well, how come you're getting tens of millions of evals per second, even though they're going through the...
Oh, because
they're sent through one by one.
Because it's vectorized. Like the compiler vectorized it for us.
Okay.
And also you're using Chebyshev a lot, which is on a degree 16 is pretty fast. And the way this Chebyshev is implemented is actually the second part, which if we want to go through, we need to go over time. Let's see. OK, so let's go back to my GitHub, and there is another link here that is marco.godbolt something. Yeah, it's a hash, so you kind of need to go over my GitHub to get it. So while you all go into this page, I will like go over my slides. I have like some slides.
So what's the name of the file name in your GitHub that contains the URL?
Oh, it's in the README, so you'll see at the top of my README. There is marco.goldbot. OK. So what is SIMD? I'm not going to like spend too much time on this, but basically it allows to apply the same instruction over multiple data. So if we look at this chart over on the right, for each clock cycle, T0, T1, T2, T3, instead of getting one result, we get 4 if we use SIMD, at least for the example I gave you. That's all there is about SIMD. When can you use it? OK. I listed a bunch of things here, mostly for reference. I'm not going to go through all of them. But the main thing you want to look for is independent operation. So if you can execute your for loop in any order, then you can sim date. Usually that's the rule of thumb. And then also you have a for loop that is big enough because there is overhead into moving data from scalar to vector registers and back. So you want to like have a for loop over lots of elements. If you have a very small for loop, you might actually get a slowdown because you're spending more time moving data among registers instead of actually doing what you're trying to do. Okay. When it's worth it, that's all I said. It's just for completeness because I'll upload the slide somewhere. So simmed in something is not complicated once you have a recipe for it. Like, that's my take. When I first tried to learn it, nobody taught me anything, so I spent quite a bit of time on figuring out. But there are like a 5-step process, and I feel like a motivational coach here, like, you know, like you can do it, you know, all these things, you know, that you can do it. You know, you can apply these 5 steps and you can get things done. I don't even remember which are the 5 steps, but I wrote it down. Okay, step 0, because you're a computer scientist, and we don't use Julia yet, is choose the right algorithm. I think this formula over here has been flashed to you today at some point. That was not coordinated. Okay, so to evaluate Chebyshev polynomial of the first kind, usually known as T of n, either we use the recurrence relation, so we start at T0 is 1, T1 is x, and then n plus 1 is distinct. It's a recurrence relation. You can write a recursive function that does this. The good thing, this is, in terms of abusing notation here, requires 3 flops per iteration. So if your size is n, you do 3 flops. Barycentric interpolation, on the other hand, does 5n flops each iteration plus 1 extra we have. So in theory, barycentric interpolation should be 2.5 times slower. Something like that, or 1.5, something like that. Doesn't matter. But the good thing about barycentric interpolation is that this summation, as we know from primary school, I guess, summation are commutative and associative. We can do this in any order. That basically means that all the iterations on the for loop that we have from 0 to n are independent. We can do that in any order, which basically means that the second algorithm can be simmed. The first one, not so much, because it's a recurrent relationship, so you need the result of the previous iteration to compute this iteration. The previous result feeds into this iteration. Okay. So if we go into my thing over here, which I might do this, okay. So what do we have here? A bunch of code, no? That I unfortunately cannot show, because if I make it too small, you might not read it, but we can try to make it a little bit smaller. This is too small. I think this is reasonable.
Yeah. Fold the right side briefly.
We can fold the right side briefly, but we have the code that we need to see here.
Yeah.
So if we look at here, I have 2 implementations. This is the implementation that uses the recurrence relationship, and I'm using a for loop here. And this is called, I guess, Cheb. Very, very intuitive name, I would say. Then I have like bar Cheb that use barycentric interpolation, and this is the for loop for this other thing. You know, all this math we are flashing, you know, is just a couple of for loops. Nothing is complicated here. Okay, so if I ask Google Benchmark to tell me in big O notation what is the algorithmic complexity, we notice that for the recurrence relationship, we have 3.37n. So it means that it does 3.37 assembly instruction for a polynomial of degree n. Cheb instead, apparently, does much faster. This is just a bad draw in this compilation, I would say. Probably I'm going to rerun this because I don't believe that. Library was OK. Program returned 132. And why are you not working? I have no idea. No, this is fine. Google Benchmark was built at debug, but I don't understand why it's causing issues. I guess because we are all loading the same server. Okay, now we have something that I believe. Now we get 148n for Cheb and 4.58 for bar Cheb, which is pretty similar to the operation I showed you before. So if we look at the grid 128, using the recurrence relationship takes 200 nanoseconds. This other version, 206. Pretty close in this case. And after everything, there is like a test that shows that everything is giving the right result. OK.
And what order or degree are you using?
It's written here like 16, 32, 64, 96, 128. Which is, if you're using barycentric, 128 is not that uncommon, I would say. You might even get to thousands here. Sure. Like if you're using Cheb-Fun, 10,000 elements is pretty common. OK. OK. Now the question is, how do we vectorize this easily? What is the 5-step process? I think it's 5 steps. We will figure out to vectorize this. OK. If we go back here, there is another class here called barcheb here. And then we have barcheb simd. I wonder why. I already populated 2 shorthands here for you to follow along, which is how many simd lanes we have, how wide is the vector instruction. This is something that already, and just for your sake and my sake, we are using an interface to SIMD. We are not writing intrinsics by hand because it's a terrible job. We are relying on some sort of abstraction that gets the job done. OK. So this is the first step. We need to figure out how many lanes we have available to us. And the second step is to, first of all, we need to truncate the number of iterations we have to a multiple of the SIMD lanes so that we don't do out-of-band accesses. Because imagine, if I'm iterating over 10 elements, no, and my SIMD lane are 4, I will do 4, 8, and then 12. So I'm going to have 2, like the last iteration, doing an out-of-band memory access, which is, if you're lucky, it's going to crash your program with a meaningful error. If you're unlucky, it's just going to proceed and give you wrong results, and you'll have a hard time figuring out why. Use sanitizers. That will tell you that you're doing something wrong. OK. And then, once we know how many iterations we do, we split the loop in 2 loops. One loop goes up to the multiple of SIMD lane that we are allowed to go. And the other loop takes care of the tail. Basically, it starts from the truncation up to the end. And the first exercise here is to do that. So we need to like take this loop and split it into 2 loops. Simple as that.
So we're editing barcheb SIMD.
Yes, you're editing barcheb SIMD. I mean, you can edit barcheb, but you know, like it's going to make things a little bit inconsistent. Whoever has done already like this splitting can go here on share, click on short link and Slack me, and I'll open it up instead of me having to write so that I can answer questions. Questions so far?
We're not making a running code yet.
No, it doesn't matter that as long as you split the loop into 2, it doesn't matter that the results are not correct, because they're not going to be correct until we are done with. Like, there is a point where we are going to make a breaking change. Because, for example, when you split the loop, no, when you're iterating up to the SIMD width, up to the multiple of SIMD, what is your increment now? You increment by 1 or not?
Okay, so writing a nested loop, 2 nested loops.
Oh, if you want to make it work, there is no need to write the nested one. You just split it. There is no. I don't really need a working code here. I just need 2 separate loops, where this one is basically unchanged. Okay, because we are running out of time, I'm gonna copy paste from my solution and show you what I meant by that. So the first thing is we figure out what is our multiple. This is a pretty slow way of doing that. There is a better way of doing that I'm going to punch in. And the second is just you have 2 for loops. With the first one, we leave it unpopulated for now, and we are going to put things there as we go. I'm going to share the slides, so don't worry about having to take notes or anything. So my way of truncating usually is to do this. We go is n, big N, and then I do this usually. This is somewhat redundant. So who thinks this is undefined behavior?
Well, I don't know what that's not human readable code. What does it do?
You know what is the minus of a power of 2 into complement?
It's a whole bunch of 1s and a 0 in the middle.
And then you start getting all zeros. It's all zeros.
Okay.
So basically, with a bitwise AND, because I know that SIMD width is a power of 2, I'm zeroing all the extra things in AND that I don't want to. And I'm exploiting the power of 2's complement. I'm a huge fan of it. And then the other thing I do usually is to have my index around, move the index outside. Usually I do this, then I do this, and then I do like this, and then I just change this to trunk N. And then I just comment out the code here. That's my way of doing that. And then I do plus SIMD.
The trunk N is the end that the SIMD stops at.
Yeah. Yes, I called it trunk N. You can call it whatever. I guess calling it, I don't know, calling it like Jonathan probably is not very intuitive. I call it ntrunk. Maybe it's easier if I am consistent at the very least. Okay, this is the first step. Once you are here, you are basically done. Okay, I'm going to show the code again once I go back to my slides. Okay. This is more or less what I was expecting. Be careful that we are incrementing by the SIMD width. This is usually the pitfall. I forget to increment by SIMD width. I increment by 1 here, and I start getting a bunch of garbage out of it. And then I'm like, oh, what's going on? Yeah. And it's not even faster. Yeah, the increment is wrong. OK. This is how we populate a SIMD register. We have a load function, which is unaligned by default. This is what you use. You use something different only if you know what you're doing. But we usually don't. So we leave it, or we cannot change something to make other things possible. So this is how we do it. We load the data into a vector register, and or we initialized the vector register with a constant. That is also possible. And for this particular example in C++, the STL containers, like stdarray or vector, I don't know what you're using here, have a dot data that gives us a pointer, because this thing to work requires a pointer. We are doing low-level things. We need memory addresses. We cannot rely on abstractions, or at least not yet. I'm building one. So the step 3 out of 5, just 2 steps and we are done, is to just populate the register. This requires just 3 lines of code, because we basically only have to load from this one, and this one. So we have 3 load and aligned. That's all we need. Nobody's typing anymore. I guess everybody did it. Okay, so what's the question? Yeah, you basically click, yeah. Or you just do dot data plus the index, which is what I usually do. So like if I were to like give a suggestion, yeah. Then you can do like things like this to move it. If you want to point them, this is the. Okay, so I need to like do it, otherwise we are gonna like. So the first thing I do usually, I move the initialization outside the loop. We need to, because our num here is outside the loop, so we move it outside, and we set it to 0. Otherwise, we have a bug. Okay. And this is replicating what you have done here. I just call it bnum and bden because it's a batch, a SIMD register. And then when you get here, we just, I want to also have a vector of our pointer in input here, just to initialize it. And then we basically want to do the same thing here. We have x, y, no? So bx is equal load xmd. Let's call load of x dot data plus I. Okay. Now we have f while zeros and we, so I'm just gonna like copy paste the code a couple of times. And what do we call this?
Is the point we can replace like w by a xmd vector of w, and then not think about it.
Yeah, I think so. If I understand your question correctly. But you can basically look at what appears on screen to have your answer. Yes, you're out. Yeah, we have only like to uncomment this code and we're done. Okay. So yeah. One thing about using XMD is that it allows us to, yeah, this is basically what I've done here, that we have all the operator overloads. So the plus works on XMD batch as it works with integer in C++, same for all the other operators. And XMD also offers you square root, for example, abs, and cos, and a bunch of like basic mathematical stuff. So even log, I think, is there. And if something is missing, open an issue, and it will add it pretty quickly because it's not complicated. So the step 5, okay, is to basically uncomment this loop, this code here. If we just uncomment it, it's going to mostly work. We are going to get an error because num is defined after here, so you need to rename this thing. But if we just uncomment the code we had here, now we just change this to B, and this xy is going to be our bx, and w is going to be bw, and bf vals is going to be like this other thing we have here. Okay? And the last thing we need is to figure out how do we convert bnum and bden into num and den, which is the last thing we did, and then we can look at the performance. So everybody's on the same page. I'll explain what that is by going in my slides. Okay. So now we have what we usually call a partial result. We have a bunch of partial results into our SIMD register, and we need to coalesce this into our final result. For what we need here is what we call a reduction. We need to sum all these things into one thing, because what we have here in index 0, we have like all the sum of the multiple of the SIMD lane, and so on, offsetted by the lane. So in 0, we have the sum of like 0, 8, 16 of the Chebyshev polynomial evaluated at these values. Then in 1, we have 1, 9, 17, and so on. XMD makes that really easy. We just call reduce underscore what type of reduction we want. Reduce add, reduce sup, reduce mul, There are many ways that this reduction can happen. If you're doing a tensor product, it's more likely that you're going to have a reduce mul, for example. So in this case, the last 2 lines we need is an XMD reduce underscore add of bnum, and one for den, which we'll call bden, which is not Biden, is bden. Okay? And our code now should just work. Will it? In my presentation works. Here it works. And if we look at the performance, we notice something interesting. This recurrence relationship takes 200 nanoseconds. The barycentric version 207, because gets optimized pretty easily by the compiler, our code takes 144 nanoseconds, which is almost like a 25–30% speed up here that we get, something like that, because 50% we get to 100. And this is pretty fast. If we switch to an older compiler, just as an example, you realize that how fast things got over time. Because when I tried this on, this is not something I believe, definitely. But yeah, it's quite a bit slower. And this makes no sense as a result. Let's try it again, because it's far too slow. Yeah, 228. So it got like 10% slower just by using an old compiler. But our code now, like, it's completely out of whack. But try that again, and it's still out of whack. Fantastic. This is not what I wanted to show you, but everybody's on this server in this room. So, you know, like, try it at home. And I can get it, like, I can try again, but we're wasting time. OK, so that's how to vectorize a loop in 5 steps. I'm going to share my slides. Usually it's easy. Usually works. It worked here with all these things. I hope you learned something. Questions? Orderings?
Let's go for drinks, and then you can ask Marco questions.
Oh, yeah.